Pendulum is one option. And what else? What was the second system that involved simple harmonic motion? A mass spring system. Very good. The reason we say a mass spring system is because the mass that's attached to the spring that is then set in oscillatory motion affects the motion, whereas the mass of the bob, right, the object at the end of the pendulum, does not affect the oscillatory motion. It's independent of mass. That was a big conclusion we drew in the lab and also in our algebraic form. We ended up getting, I think it was 2 pi root g over L, or L over g, I forget which way it is. But the idea was that the mass had no effect on a pendulum's motion. Okay, L over g, that's what it is, okay? So we've got this, we've got tau equals 2 pi root L over g, and tau equals 2 pi root m over k. So the idea behind simple, and I should have finished the topic heading there, harmonic motion, is that if there was no friction involved, what would happen with these systems? If there was no friction on Earth, focus back there, guys, whatever you're doing, what would there be?
Would it like never stop?
Yeah, it would never stop. And that's what simple harmonic motion is. Simple harmonic motion is the concept that under no external force, this motion would be oscillatory. It would be periodic. I was cleaning out part of my house over the weekend. And I was going through, so I lived in my grandma's house. I was going through all of our old stuff. And I was thinking of this class the other day because of what happened, I'll tell you. So, I don't know if anyone's ever seen this before, but if you ever, what do they call when you open up the box and it starts like it's a little jingle?
Jack in the box.
What is it?
Jack in the box.
A jack in the box, but it doesn't pop up. A music box. Just a general term. Okay. Yeah. Have you ever seen the inner workings of a music box and how it actually makes the sound? Does anyone honestly know? Have you ever taken it apart to see all those little jingles? How does it work?
Don't they have like different types of like they have like a metal or something and different size, and when you roll it, it turns, and whatever like level or thickness it is, it makes that noise with a little kind of like a keyboard thing.
That's exactly it. And it's the coolest thing. It's this little cylinder that rotates, and it's like a little piano. And you know how a piano you strike the keys? The cylinder that's rotating has little imprints on it, little dots. And as it rotates, the dots flick. They literally like flick the key, and you hear like bing, or different frequencies. And that's what causes it to be periodic. And I always wondered, like a music box, after a certain amount of time, it gets back to the beginning, right? The tune repeats itself. It's not like a new tune every time. You wind up the music box, you open it up, it goes through this whole little thing, maybe this little, like, sometimes a ballerina that sits there and turns, or a merry-go-round. And what happens is the sound eventually repeats itself. And it's because of what Kat was just saying. It's this metal piece, again, that has these little, like, bumps in it. And the bumps are at different locations. I should bring it in to show you guys. It's actually really cool. The bumps are at all different locations. And as it rotates, depending on when the bump hits one of the keys, it flicks that key, and you get a sound at that certain pitch or frequency. And the idea behind it is really, it's periodic. It's simple harmonic. The idea that it's cyclical. It continues to occur. So here for these examples here, the mass, you release it, it will continue to oscillate over and over again. Some key characteristics about this. For a mass spring system, let's say that this is the normal spring length right here. Oops. Let's move that up a little bit. If that's the normal spring length and you compress it so that this is now the spring, remember that your compression is defined as x, right? X. And x is the distance between the centers of the objects or the fronts or the backs. It doesn't matter, but you have to be consistent. So if I measure that, let's say that from here to here, I measure this to be 7 centimeters. And then from here to here, it's 4 centimeters. That's a 4 right there. Okay, so this length is 7 to the end, this length is 4 to the end. Clearly the x value is going to be 3, just the difference between the two. Remembering that x is how much the spring has been compressed or extended. If this is in simple harmonic motion, recall from your trig that you know and the simple sine waves you looked at. We looked at like the amplitude and stuff. This out here, the amplitude, okay, this would go, you'd stretch it, you compress it to 4. When you release, what's going to happen? You compress it all the way here and let go. What happens then? Yeah, it shoots out. How far does it go? 4. It starts, it's going to be compressed to a length of 4. It started at 7.
11.
So how far is it going to go? Not 11, 10. You have to look at the difference and tack on the difference over here. So since you compressed it 3 centimeters, it will go, as Kat said, to 10, which is 3 centimeters further than where it started. So you know already that this spring is going to oscillate between 4 centimeter length and 10 centimeter length over and over and over, passing through what we call the free length, aka the equilibrium position. When this spring is compressed, which way is the spring pushing? Give me a directional, left or right. When it's compressed, which way is the spring pushing? Right. When it's stretched, it is pulling back left. So whenever the spring is stretched or compressed, there's a force acting on it. God bless you. There's a force acting on it. So it's not in a state of equilibrium. It's at its, God bless you, when it's at its extents. When it's at the full compression or full expansion, it is not in a state of equilibrium. When it passes through the middle position, known as the free length, it's in a state of equilibrium. That's when the spring is not really pulling or pushing, but because it has velocity at that point, it continues to move over and over. Okay, so that would then stretch, and I'll draw a third one in blue. And this distance from here to here, again, would have to be 10 centimeters. So you compress it, the spring force is positive to the right, you let go, it shoots off. It slows down, it slows down, it slows down. Oh, sorry. It shoots off until it reaches equilibrium, it speeds up. And then it passes equilibrium, it slows down until it's fully stretched to 10. It stops, and then it starts to pull back. It speeds up, it speeds up, it speeds up till it's the middle. And then what happens to the spring? It starts to compress the spring so that it slows down, slows down, slows down. Speeds up, slows down. Speeds up, slows down.
Wait, what's the middle called?
Equilibrium position or free length. The free length of the spring. 7 centimeters is the free length. 10 and 4 centimeters are like the max and min positions. The amplitude would be 3 centimeters here. How is this all related to this formula here? How is this related to this formula here? What does tau stand for? What is tau? This symbol right here, tau, what does it stand for?
The period.
The period length. And the period, if you remember, is the time it takes to complete one full cycle. So if I compress the spring and let go, the time it takes to go like this is the period length. Okay? To literally extend itself fully and come back to where it started, that is one period length. God bless you. So, the characteristics, why is that funny? That's a funny sneeze, all right. I mean, everybody has a funny sneeze. My cousin has the weirdest sneeze. It's like, you think like the wall's falling down every time she sneezes. Not the cousin I live with, another one of my cousins that is older than me now. When we were kids, we used to joke, 'cause she would sneeze and you should, and everybody would look like, okay, relax. You could sneeze like at a normal level, but sometimes you obviously, you can't control. Like I've sneezed before and it comes out high pitched, and that's kind of weird. Everybody's done that once or twice. So, if you want to calculate the period of oscillations, it is dependent upon two things, the mass and the spring stiffness. And think about it logically. If the spring is a stiffer spring, a stronger spring, it means the K value is higher. Look where the K value is. The K value is indirectly related to the period. And think about this logically. If I had, let's see a good example. Perfect. This broom. It's kind of dirty, but we'll make it work. Alright, take a look at this broom. Take a look at this bristle right here. I pull down on this bristle and let go. That's pretty much, this is a rotational spring really, but it's what a spring really is doing. This is fluctuating back and forth until it reaches equilibrium. But this is a rotational spring. Does everybody see what I'm doing right now? The time it takes for this to settle down is the period. Well, the time it would take to do one oscillation is the period. If this wasn't, whatever this is, it's plastic actually. Yeah, it's a plastic. If this wasn't plastic, if this was a very, very, very stiff metal, and you tried to do this with the metal and let go, it would take a lot less time. It would go real quick and it would settle out. But when I do this with the plastic, it takes a little bit of time for it to finally settle out. Because there's a little more fluctual rigidity to it. It can bounce back and forth a little bit. It's not as strong. But metal, a metal rod that would be stiffer doing that too, it would settle out real quick because it would have a lower period length because it has a higher K value. Again, the K value is indirectly related, whereas the mass is directly related. If it's a heavier mass, and that's why has anyone ever, oh yeah, you've ridden in like buses. I would say ridden an 18-wheeler. That'd be kind of weird. But in a bus, right, a coach bus, when a coach bus hits a little bit of a bump, sometimes it takes a little while for it to oscillate a little while because of the mass. The mass of a coach bus is so much more than the mass of like a car. A car's shocks don't have to be very strong for it to control the vibrations. A bus needs very strong shocks. If the shocks or if the suspension on a bus is old, if it's an older bus, maybe you get on like a Greyhound bus or a Peter Pan, whatever, like an older version of their bus, not a new one. Sometimes if they're not really maintained well, what you'll notice when you hit bumps, it oscillates for a while. They're not big oscillations, but it oscillates for a while. Heavy mass prevents big oscillations, but the oscillations occur for a long time because the period length is much longer for a larger M value here.
Does that have something to do with like older buses have the middle that's kind of like an accordion, or is that just for like turns and stuff like that?
No, the middle for the accordion helps with the turns. For the long buses you're talking about?
Yeah, like they used to, but how come they don't do it anymore then?
They do still, but it's limited. The middle part of it, it's really interesting. That's like a rotational spring, what's happening there. When the bus turns, there's some force that's also pulling it back to the way it was. That's why the middle you're talking about the middle when it rotates, right? Yeah. And the back of it, though, has to continue to sweep around the right turn. You can't use that in a lot of streets, like in New York City, so it's only select buses that have that. For example, anybody take a LaGuardia bus from 125th ever? It goes right to LaGuardia from 125th? No one's ever taken it before? You fly out of LaGuardia ever?
I have.
Okay, once maybe, yeah. So
I really have.
it picks up at 125th and it's the long bus. Why? Because it's mainly on a straight road the whole time. It goes over the bridge, it stays in Queens, but it continues east almost the whole way.
Yeah, but the city buses used to always be like that, and now they just don't do it anymore.
Were they as big as those though? The one on 125th is like 2 buses combined. It's huge. It's like the length of 2 buses. The old ones, were they that long actually? I felt like they used to have buses that were a little bit longer than the normal bus with the middle piece, but not like these new ones. The new ones are literally 2 buses length.
Old buses are smaller.
The ones that used to have it in the middle, they were a little shorter, but they still had it. But it is involved with, period and frequency and stuff. That's involved for sure because that middle piece has to respond. So there is some, there's an inherent K value. It's not a K value like a spring, but it has to do with the actual system. There's a damper, there's a spring in there, there's something that controls the motion. A little more advanced than this, but the topic of simple harmonic motion is extremely important in order to make a bus that would behave in that fashion. So again, this is the mass being directly related here, and the K value being indirectly related. What if you didn't have the K value? What are the formula from your formula sheet involves K? There's another one on your formula sheet that might be useful. It involves K. It's in the same, area on the formula sheet if you're looking at it, or if you remember. What other formula involving this material involves K also? Nobody remembers? I thought maybe somebody would remember off the top of their head. Marianne?
Something equals kx.
Yes, something equals negative kx, yes. What is that something? F? Spring, good, Fs. Fs. The spring force. So if I stretch a spring by some quantity x, and the spring has a rigidity k, I can calculate how much force the spring is pulling back with. Whose law is this? Everybody remember whose law this is? Whose?
Hooke's law.
Hooke's law, very good. Which it comes from Newton's law. It's not Newton's law, but it does come from Newton's laws. It's derived from there. So Hooke's law tells us that the spring force is in the opposite direction of the expansion or compression, which makes sense. If I pull on the spring this way, which way does it want to pull? The other way, back toward the left. If I compress the spring, it wants to push back to the right. That's where the negative sign comes from. Because the direction of x and the direction of f are always opposite each other. Always, always, always. Always opposite one another. So in this first example, let me point right here. Take a look right here, please. the compression would be -3 centimeters because I'm going back. Over here, though, it would be an expansion of +3 centimeters. If I plug in a positive for x, k is always positive. So if I plug in a positive for x, I'm going to get a positive, positive, negative. So this whole thing is going to be a negative force, which makes sense because if I pull on the spring this way, it wants to pull back this way. That's why you get a negative force, because the force is the direction to the left. If I compress the spring to the left, it pushes back to the right. So if you are in a situation where you didn't have K, say you had the mass was 40 kilograms, but you didn't have K, and you were told when the spring is compressed by, 2 centimeters, when the spring is compressed by 2 centimeters, the force felt in the spring, it should be negative, it's compressed, the force felt in the spring is 40 newtons. If you're given that information, you need to solve for K first. There's a negative out there still. Okay? The double negative will give you a positive K value, clearly. Solve for K, and then plug it into the formula at the top. This was very much a two-part problem, mathematically. Okay? Usually I did not give you here's F, here's X, find K. It was usually all right, find the period of oscillations, or find the mass. But to find the period or the mass, you needed to know what K was. So maybe part A was find K, and part B was figure out that second component. All right, with the final, I will try to give you steps so that it kind of guides you along the way. So for problem, in this case, ask you for period, you need a K value. Most likely part A will ask you for the K value. What happens if you can't get part A? What should you do? You shouldn't just give up. If you can't get part A, you forget completely how to get the K value. Pick a random number. But something don't pick, if you pick a negative K, I'm going to get upset because K can't be negative. So don't pick a completely random number, but pick a sensible number, right? A positive for K. Doesn't matter what positive number. But pick a number. K is 4. All right, K is 4. Now I can do part B based on my answer to part A. So you don't get double jeopardized. Because if you can't get part A and it's based on part B, or part B is based on A, you really can't do it. So as Nora said, pick an arbitrary, sensible number for the first part of it.
But if you can't find K in part A, couldn't you just find it in part B?
No, because we're trying to find the period. Remember this problem, I was trying to find the period. So yeah, Paul, if we knew the period, absolutely you could find K, but then you wouldn't have needed part A. Okay? Yeah, so it would be a part where you need part A to get part B. It's not like you can use part B alone. How is this analogous to the pendulum system? Let's take a look at that now. Here's our pendulum, right? It wants to move this way because gravity is the restoring force. Remember, the spring force is the restoring force for a mass spring system. Gravity is the restoring force for a pendulum. Here's our formula. Okay, as the length of the string gets, if you can remember this, by the way, before I was forgetting whether it was G over L over G. The length of the pendulum, as the length gets longer, it takes longer time. So the length has to be in the numerator. It's directly related. You did this in your lab. In your lab, you had one with a 15.5 centimeter length and one with a 31 centimeter length. And you analyzed the difference in the period length based on the change in L. There's no mass involved here. The mass at the end of the pendulum does not affect the system for simple harmonic motion. If you go on to study engineering, you learn how the mass does affect another part of it. Okay, it affects what's called your ordinary differential equation of motion for the whole thing. You do involve mass. But that's because when you study engineering and you study more science, you're going to learn about air resistance, how that's a function of it, and that involves calculus. So this is all neglecting air resistance, all that stuff, so we don't really have to worry in this case about the mass. What was funny about the word calculus?
Oh no, we're gonna for
Okay.
It's an inside joke, we don't understand.
You guys are funny. So what is this angle theta known as? What is this angle theta known as? The what? Yeah, the initial angle. Good. The initial angle. Now, with a mass spring system, guys, you should be looking up here. I don't see enough eyes. I'm not writing anything. I'm not saying stuff that needs to be written this moment. I see too many hands. This is a review week. Please, heed this advice. Review now. You have to study a lot less later. Okay, somebody said it the other day, and I was like, finally, it's been true all year. Pay attention to class, less work outside. A lot of you do other stuff and then try and catch up outside. You become inundated and you can't sleep and stuff. And you run out. No, seriously though, people come in and say, I watched 5 of your videos last night. I'm like, that's great and all, but you shouldn't have to watch 5 videos in one night. What are you doing in those classes if you're watching 5 videos? Theta is the initial angle, or the initial starting point, whatever you want to call it. But the idea mathematically is that it represents the amplitude again. For a mass spring, the spring starts here, right? This is the normal length. If I pull on it this way, the difference is x. That was the amplitude. Theta is like your x in this case. Theta is your amplitude. And this mass, or this bob, whatever you want to call it, is going to do this. It's going to make itself up to the same theta on the other side. Assuming what? Assuming there's no friction involved here. If friction is involved, what's going to happen? If friction is involved, what's going to happen?
It's not going to go as far up.
It's not going to go as far up. If the angle you start at was 40, you might make it to 38. And then the next one might make it to 34, and then 29, whatever it may be. Okay, the idea behind this is that a pendulum loses energy in real life to some form of loss, whether it's some sort of friction in the actual pivot point or air resistance. Either one, it's losing energy. But in simple harmonic motion, we assume no loss of energy, so we can make the statement that theta 1 equals theta 2, if you will, or whatever. The black written and the red written theta here are the same. For simple harmonic motion, theta is the amplitude. And as we said a moment ago, L is directly related. This is conceptual. I don't want to say all. 2/3 of your multiple choice, you should really be using formulas to help you with a lot of the time. I ask a lot of multiple choice that are things like, as the length decreases, or as the length goes up by a factor of this, what happens to the period of oscillations, those kind of questions. You should definitely be referencing these formulas on multiple choice also, but you are not really going to have to directly use them. And you have to use the concepts of them. Or remember, from your lab, think about it logically. If the length of the pendulum string doubles, it's going to take longer time for the oscillations, right? A short pendulum does this, back and forth real quick. A longer pendulum takes a lot longer time. So we know clearly that the length of the pendulum affects the actual period of motion. Okay? Other questions on simple harmonic motion? I forget who posed this question, but somebody posed this the other day. Okay. What else? What else you guys want to do? Last time did we do forces last time in here, or did we do projectile motion? Circular motion. Okay. Yeah.
Remember Coulomb's law?
Coulomb's law. Okay. So Coulomb's law tells us, we had 3 formulas related in that area, right? You're talking about Fe equals kq1 q2 over r squared. This one is squared, right, Marianne? Am I correct?
Yes.
Okay. Because one of them is not. I forget which one. So, K is a constant like G. It's a universal constant. It's called Coulomb's constant. Just like G is really Newton's constant or Newton's gravitational constant. What are Q1 and Q2 in this problem? And they're not He loss, remember. He loss is the capital Q from Q equals MC delta T or Q equals ML. What are these?
The charges.
The charges. So I clearly need to have 2 charged particles. Is that clear right away? You cannot have a force of electricity between 2 particles if one of them isn't charged. Magnetism is a little bit different to talk about. With magnetism, we can talk about magnetic fields. This, you can create an electric field around a single charge, but there's no force that exists. So if I had a single charge, right, a single charge is this formula here. That's a single charge. That's the electric field in newtons per coulomb. So if you have one single charge Q, it produces an electric field around it with a value or strength of capital E. That's the field strength, E. R is the distance from the charge, the source itself. Now, if we introduce another charge into that field, we get back to the first formula. So here, let's say this is, we'll call this Q1. So in this scenario, there's some particle Q1, and it's giving off some sort of electrical field. Let's say, it doesn't matter the value, I'll leave it for now. But there's a field that exists around this at a certain distance. Depending on how far we want to go away from it, we then take another charge and place it somewhere. Well, this Q2 is now in the range of this field that Q1 created. Remember we called Q1 the source? The source is emanating this electric field. Q2 comes into the range of the electric field. As a result, it feels a force. Either it feels one of two forces. What kind of forces can it feel? For electrical charge, it can feel this or this. For repulsion or attraction? Repulsion or attraction? Well, how do we remember which is which?
Well,
Whether it's a repulsion or attraction.
repulsion pushes the particle away, and attraction, attracts one.
And how do I know from the actual numbers in the problem to know which it is?
Repulsion would be negative.
Yeah, but make it even easier on you. We will get a product in the end, but the Q values, what about them?
Other opposites
For
for repulsion.
attraction. Opposites attract, same repel. Remember magnetism? So if Q1 and Q2 are the same sign, you're going to have repulsion. So you'll get a positive force as an answer. If they're the same sign, like if Q1 and Q2 are both positive, Fe is going to be positive. So when Fe is positive between just 2 points, you have repulsion. When Fe is negative, you have attraction. The only way you can get a negative Fe is if Q1 and Q2 have opposite signs. If Q1 and Q2 have opposite signs, it's attraction. So opposite signs means a negative force. So when this answer you get up here turns out to be some number less than 0 or negative, it means attraction. Okay, this occurs when one of them is negative and one of them is positive. If they're both positive or both negative, this becomes, instead of less than 0, it becomes greater than 0, and that would be repulsion. Now, I'll tell you at this moment, you're not going to have to do one with 3 charges. The math behind that was almost like a 10-minute process, so I'm not going to put that kind of problem in your final. So anything that's a really, really extensive problem is most likely not going to be in the final. Most of them will be, not simple, but simpler than that 3-charge particle problem. So when you're studying, go over the 2 of these for now.
On the final, would there be a problem where you have to place 3 particles?
Sure, I might say how far away should the other particle be? So you're determining R.
Okay.
You could have to do that, but I'm not going to have one where it's 3 particles on a number line or there, and find your overall force on one of them as a result of the other 2. Just because the process in that problem is 10, 15 minutes to go through the free body diagram of each, all the math. So what I'll most likely end up doing is something like this. This should be known conceptually for sure. Easy multiple choice problem. Charge all these 2 particles as follows. What could you conclude as a result? Particles are attracted to each other, they repel from each other. The particles do not move, and not enough evidence is there. You know what I mean? That's an easy multiple choice. It's the same as magnetic fields. Both of the poles are north, they're both toward each other. What does it feel? Bless you. It feels repulsion, because the same signs repel. Mathematically, units of Q are coulombs. A lot of the time, though, you're given charges in microcoulombs. Remember that little mu symbol, micro? What does microcoulomb really mean again? Close? -6. Micro, think about a microscope. You can see things at a level of 10 to the -6. That's where it comes from. So, if you see that your charge is given in microcoulombs, you need to convert. So if Q1 was 3 microcoulombs, that's 3 times 10 to the -6 coulombs. If Q2 was 4 nanocoulombs, that's 4 times 10 to the -9 coulombs. Take this quantity, take this quantity. R is the distance between them. Plug that in. K is on your formula sheet. Okay, K is on your formula sheet. So to find the force, plug them in. If you want to find the field produced by the stronger charge, which charge is stronger? Be careful here, please. Which charge is stronger? Josh.
3 times 10 to the -6.
Good. Don't fall into the trap and see 4. Think, 4 is bigger than 3, so it's bigger. Micro is 10 to the -6. Nano is even smaller, 10 to the -9. So 10 to the -6 is a bigger value, so it's the exponent that governs here, not the numerical value in the front. Okay? So as a result here, what we'll notice, if you wanted to find the field produced by the source would be Q1 here, the stronger of the 2 charges. You plug that in for Q1, plug in Kc, Figure out how far away you want this to be. Maybe you want to know how strong is the field 3 centimeters away. So plug in 0.03, square it, you can get your electric field. Your electric field is measured in newtons per coulomb. Your force of electricity is measured in newtons. How do I remember newtons per coulomb? Is an easy way to remember. Anybody know? The force, you know all forces are always measured in newtons, right? So that one, can I assume you memorized? Anything that says force, bless you. Like the top there is measured in newtons for sure. How can I remember that this is newtons per coulomb? How do the equations differ? What's missing in the second equation that was in the first? What's missing in the second equation that was in the first? Another charge. What are the units of charge? So this is no longer newtons, it's newton per coulomb because you're missing a coulomb. Think about it. This has to become newtons per coulomb because they're missing a coulomb up here to cancel with that coulomb. So if suddenly the Q goes away, it means that the new units are no longer newtons, but newtons over whatever the Q units were, which are coulombs. I'll put units on the side over here. Okay, those are the units that I'm talking about there. That's the units for electric field strength, right here, and electric force up top. Vocabulary is so important. There is a big difference between electric force, electric field strength, and what was the third that we did? There was a third formula like this. Anybody have a formula sheet? Look at this section where I had these two formulas. There was a third. Come on. Anybody remembers it? It's measured in joules. What's measured in joules? Energy. So what was it? Do you remember? But do you remember what it described? The potential difference between two electric charges. Look on your formula sheet. You'll see another formula that says PE equals K Q1 Q2 over R. It's the potential difference between two charges. Okay, and this is measured in joules. All right. What else? How are we doing on time, guys? Good. We still got a few minutes. Another topic. It's another topic that you maybe struggled with throughout the year. Paul.
Magnetic fields.
Magnetic fields?
Yeah.
Okay. So for a major formula sheet open, I'm trying to recall. F equals BQV, did I give you, or did I give you it the other way? How did I present it?
Equals F mag.
What was it?
B equals F mag Q.
Okay, that's how I gave it to you. Good. All right. So, if we're looking at magnetic fields, first, B is like capital E from the last slide. What was capital E on the last slide again? The formula that said capital E equals. That was E stood for what again? Field strength. Electric field strength, right? B is magnetic field strength. B is like E from the last slide. Again, it's the same thing. They're analogous to each other, really. B is the magnetic field strength, though, this time. And F is still force. Instead of electric force, though, I wrote F mag for magnetic force. Q, charged particle. So we still have a charged particle here. And V is velocity, not volume, right? V is velocity. So for these problems, the whole concept was, if you have a charged particle in a magnetic field, it will feel a force if it is moving. What if it's not moving? Why won't it feel a force? More mathematical than conceptual. Mathematically, why would you feel no force if it's not moving?
Because then you get F over 0.
Yeah, you get F over 0 here, right, wouldn't you? If it's not moving. You get a 0 in the denominator, and you multiply it up, you're going to get B times 0, F becomes 0. Because if you solve for F, F equals BQV. F equals BQV. So if velocity is 0, you clearly don't have any force. If there's no charge on the particle, if there's a particle moving through a magnetic field that is not charged, it will not feel a force. Again, if it is not charged. So we have those two main things, and obviously, clearly, you need to have a field. So the field has to exist, the particle has to be charged, it has to be moving for this force to be felt. The other thing we did with this The only other real thing was, remember this? Right hand rule. Which some of you do a really great job on the test. I'm really butchering this stuff, so let's go over this. What do we got? Fingers pointing in the direction of the field. That's B. Let's draw a diagram actually, because I think it was actually interpreting the diagram that people confuse most. So let's say the diagram looks like this. Here's the particle. Particle is moving to the right. The velocity v. What does the b stand for if I just draw it there like that? How do you interpret this? Because some of you interpret it correctly, some did not interpret it correctly. If I just put a b there, how do we know which way b is referring to?
By the way, so the X is when it's going into the page.
Into the page, okay? Again, the X's and the O's mean into or out of the page. If I had put F there, it would mean the force is coming into the page or out of the page. I put a B there, so the B refers to the fact that the field is into the page. Take your fingers, put your fingers into the page. Take your thumb, point it in the direction of the velocity, so flip your hand up. Thumb goes in the velocity's direction. Your palm always points in the direction of the force felt on a positive particle. So this positive, assuming this particle is positive, although it's moving right, it would feel a force pushing it upward. If this was an electron, which way would it feel force? Downward. Okay? Again, depending upon what's given, you have to adjust the problem. Make believe now for a moment that that had not been B. Erase the B and put F there. If F is the force, and the force is into the page, your palm needs the facing of the page. So start by doing that. Then you have to have the velocity facing the right. So you need to rotate your hand like this. It's a little bit awkward to hold your arm like this, but your palm is still into the page. Your velocity is to the right. But which way are my fingers facing?
Down.
Down. So that means that B would be down in this case. Remember, B is the way your fingers face. F is the way your palm faces. V is the way your thumb faces. Okay, you just got to practice this more. So if I write F there, know that that's the force into the page. Put your palm into the page, your thumb to the right. The field acts down. So B would go downward. Okay. How much time we got? One more topic, maybe. 1 minute? Any other questions right now? Oh, tomorrow. Actually, this is a good point. Perfect. Then we have a minute. Tomorrow, here's what we're doing. Tomorrow's egg drop day. Okay? So, you guys meet 7th period. Luckily, the other class meets 5th. So we're going to have it all set up already, actually. So we don't have to worry about setup. But we have to worry about takedown afterward. So, easiest way to do this. What do you have before this class tomorrow? Do you know? Before 7th?
Free.
If you have free, it'd be great. If you do have free, what I'd like you to do, if you have free, send somebody in your group up. You know where the projects are, right? They're in the closet over there, which I have to mask them still. Did anybody come in to mask them?
To what then?
Weigh them? Mask them?
No.
You can do it after this.
Okay. I might even just do it myself then. If you guys have free time to come in and do it. I know the lock has been locked, so we can't get in there. So I'll unlock it. Tomorrow, if you have a free before this, at the end of the period before class, come up, get your project, bring it right into the jugular. Okay, all you have to do is be in the jugular with your project. If you don't have a free, come up, get it right away, hustle back in. Okay, we're going to have an order in which we're going to be going tomorrow, so I'll pick out of the hat ready.
What's the weather like tomorrow?
I hope it's good. I haven't looked at the weather at all. If it rains, we got to switch to Friday.
Tomorrow's just cloudy. It's cloudy.
If it's drizzling, we'll be out there.
Yeah, it's just clouds.
If it's drizzling, guys, we'll still be outside. So if you really want like an umbrella, it's drizzling, bring one.
Bring a raincoat.
It would have negligible effect. I will assume negligible effect. Blame it on the rain.